started from phase 9. Okay, so we had the notion of the number of pages, and they will start from some address of a 4K byte interval. And so we're going to revisit the exec service to do it differently, to make the virtual space running phenomenon happen. It's an illusion, but we're going to make it happen in exec service. Okay. So exec service, of course, we need to allocate number of DRAM pages. For the purpose of building the runtime for the process, okay, for the round pit, that is. So that these 5 DRAM pages will have numbers. So we record their numbers in the PCB of this round pit. Okay. So this is PCB on the running process. To do what? To reclaim them. Okay. Some of you didn't reclaim during the in phase 9, the exit and the wait child service and exit service, that the PCB is lost. PID is not put back to the avail PQ, and then the PCB is lost. So the resources loss starts. So your avail PQ gets smaller and smaller and smaller until there's no PID. All right. Same thing with the DRAM pages. We need to reclaim. So we put that page numbers when we allocate it for the running process to switch to use the 5 DRAM pages. We got to record that in the PCB on running processes. So what does this entails? This entails that the PCB got to have not just one page number storage for storing the page numbers anymore, but we're going to have 5 in the PCB. Okay. So that is the new thing that in the phase 10. Okay. So we need to do that, and then we designate one of the 4K byte as the translation table. Okay. So we're going to put that into PCB as well. Okay. So the translation table page number in the PCB of the running process. So we are servicing running process to it becomes the virtual space running process. So we're going to add into PCB this TT. Okay, TT means translation table. Okay, the main translation table. Address translation, of course. Virtual address translated to the real address. All right. So we can start to build the translation. So we're going to build the TT. That's a DRAM page. Okay, that's one DRAM page. Okay, let's say, oh, we're going to designate this guy as TT if we allocate the first 5, 0, 1, 2, 3, 4 page numbers. And then we're going to build TT here, okay? And then TT is the main translation table. It has 2 entries, points to stack table, instruction table, instruction table and stack table. And the instruction table finally points to the instruction page. We got to start from somewhere, so we got to start with 1 instruction page and 1 stack page. And basically, we lump the data portion of the runtime of the process into the instruction page, because our instruction defined as something like child stuff, very simple. But if it does have the global variables or constants in the child stuff, it's actually defined as data, global data. Okay, so that's the follow the instruction portion. So that's what a compiler typically do. The instructions starting from the low address, and when it ends, instruction ends, and that's the end of text, e-text. So there will be starting point for the data. Okay, so the data start from here. Data means that global oral constant. Okay, global oral constant, and global things that you know, like global variables, global variables, okay. Global declares. Variables means that it can be scalar, it can be array, it can be a bunch of things. And then the constants, like if you have constant defines or macro defines, well, I shouldn't say that. Macro is already translated during the runtime, during the compile time into the source code. And then the constants like strings, especially strings. When you print hello world, embedded the double-quoted string in your program code, that's not part of your code. It actually moves out to the data session, okay? And then the address is referred to in the code, okay? So they're all the strings are moved into this area. Big or small, okay? When you have double quote, every double quote thing is going to be put in here. And then the data ends, and then it's the stack. Okay, the stack starts. Even though the usage, of course, the stack pointer comes down from here. Stack pointer starting from here. Instruction pointer start from here. Like from the first phase, there are 2 pointers that are important in the CPU, the 2 registers, stack pointer and instruction pointer. So this is confined on the process runtime. Instructions start from here, just increment. You may jump back, you shouldn't jump across this. So basically the offset of jump is not going to exceed the beginning point. The stack is also popped to this point. It doesn't pop any further than the stack underflow. Okay. So basically the phenomenon of these 2 things, like stack overflow, underflow, will be detected by OS during the runtime, and detected by hardware during the runtime. And the base pointer is where the stack pointer starts. So at any given time, main program or subroutines, base pointer is always established, static, and this during the runtime of that routine or main routine is static, don't change. Stack pointer got to be smaller than that. If the stack pointer is greater than base pointer, that's the hardware exception will occur, stack underflow. Okay. When the stack meets the data, okay, the data continue into heap. Okay. Basically, the data can continue into heap if we have heap. If you have a new allocation things, memory allocation things. So that's what the heap is. So when the stack pointer comes down and meets the heap pointer, and that will be the problem. And the e-data marks the beginning of the heap, end of the global data. So e-text, e-data, and end, okay, end of the heap, end of the heap, end, okay, END. So these three characters are inserted by the compiler for you runtime, your program runtime to check, and what are the boundaries so far with these 3 things. Basically, it's the address of these 3 things. Ampersand of this, ampersand of this, ampersand of this. The content is a character space, it's a byte, but the content is not used. It's actually to insert a variable for you by the compiler will mark the address of that character, okay, to be referenced as a global char, external char. That's the e-text, e-data, en. So this thing may move when you have a heap allocation call. In C++ Java is new. In C is the memory allocation, or character allocation, or reallocation. Okay. So you reallocate can change the current define. Like if you define an array of 100 elements, you want to change to 200, then you can reallocate it. Okay. So the array can change its size. So basically, C has these, and then the C++ and Java has these. Java inherited from C, trimmed down C++. So that's it's over there. But C used the free, okay, just like C++ use free. That will free the allocation segment. Okay. So every time allocate provide a size, okay, the size is going to have this E move up. So when stack pointer meets the end, when it push down, and that's the stack overflow. All right, so that's the process runtime. As you knew from CSC60, that's a basic runtime environment. What about the shared memories? Shared memories are mapped further out there higher, and then the shared memory segments are the DRAM pages mapped into the virtual runtime space like this. And the bottom is mapped to the kernel space. Okay. Bottom is the mapped to the necessary kernel space. Not every byte in the kernel space needs to be mapped here. And like here, what we need to map is the first 4 entries copied from the OS main table, translation table. So the map to 16 meg. We let it map 16 meg below the runtime, okay, below this runtime. This runtime is child stuff, and then this is we can set it from instruction pointer from half a gig, and then all the way to stack pointer will pop the track frame and get the arguments that will be the maximum location we set at 1.5 gig. Okay. So that's the total 1 gig space is the setup with our setup. Okay. We can change that so that we define that. Okay. So basically you can see that's how the OS exec service is going to define the confine of the runtime space virtually. All right, makes sense? So every page you follow that as a new malloc, the calloc, realloc cost is the OS service to replenish a new 4K byte page to fulfill the space here. Okay. Then at the beginning, we only have 4K byte for instruction, 4K byte for stack, and put a track frame here and 2 other things here. And then any outside needs is a page fault. Okay. Requesting outside needs a page fault will be indicated by translation tables that we're going to build, which you don't have the valid in that entry, valid code in that entry, flags in that entry. Only these 2 pages have valid signature in the pages. The mapping to kernel space is already given. So the 4 entries copied from the OS translation table into the main table we're going to create. We'll indicate those entries are valid. Okay. And we want to add 4 entries. Okay. You first want to clear it, okay, clear TT, so that all the entries are not set. And then we copy from the OS translation table 4 entries. Entry 0, 1, 2, 3. Source, destination, set. Entry still 0, 1, 2, 3. Okay. So why is that? Because every main table entry can point to a subtable. In turn, every subtable can point to 1024 DRAM pages. So one subtable can handle maximum 4 meg space, DRAM space. So 4 entries is 16, is the 16 meg DRAM space that the 4 subtables use for in the OSTT. Okay, OSTT has 4 entries point to 4 subtables. Each one points to 4 meg area. So if we copy that, then the copy translation table for that process can have the MAU translate into that 16 meg. Otherwise, those entries are empty, not valid. No translation is possible. This happens when the interrupt call. Okay. Interrupt something. When CPU execute this, CPU will look for IDT. And the CPU has a IDT register. IDT register indicates where the IDT is. Okay, IDT. And that IDT is in a very low address. And the number here will not be able to be translated if there's no translation entry to find the IDT. Okay? Okay. So CPU is given during the boost drive of the speedy that's set into the location in the DRAM where it looks for IDT. Upon any event or interrupt, either by hardware or by software call, or timer, you can argue it doesn't need to be child stop calling a system call, service call that has INT. It could be a timer interrupt, and then the timer interrupt cannot be services because the CPU cannot find IDT. Okay. Why can't it find? Because every address CPU access for is subject to MAU translation in the middle. Okay? MAU is always the guy at the door. What do you need? You know, CPU inside said, "Can you get this?" You know, and then the MAU will say, "No, that's the address you want to fetch IDT beginning address," and then we'll translate. Okay, every address in and out of CPU is translated by MAU, and after the translation, it will have the address and given to the cache. It's not returning to CPU. Say, "Okay, here's the real address. You go ahead and ask the cache." It's the MAU asks the cache. Okay, give it to cache, and then cache keeps the address, doesn't feed back. The cache will check for cache hit and miss, and only feed back the data to the CPU data bus, front side bus. Okay, so that's the all right. So it has a TLB cache system. It doesn't involve the data instruction cache or the process runtimes. Okay, so this is the MAU. Okay, the TLB structure is different from the regular cache system. You will keep the translation history there. Okay, yeah, it's a small set of entries kept from fetching the table in the DRAM before. And TLB is the cache for the translation from the real to from the virtual to the real. Okay, and initially it's empty. Whenever we set CR3, it's going to flush TLB. Okay. So to program MAU, we have two functions to help us. One is the set CR3, where the address, TT address. Okay, that's got to be a good TT, otherwise the MAU will see it cannot do it, and then you will have to, MAU have to press the reboot button on the target PC. Okay. So MAU can do that. So you want to set it with the correct translation table. That's the reason. Okay, and then you can get it. So you can get the TT in use, the address, okay, of the TT in use from the get CR3, okay, underscore. That's a void. So these two are small ASM macro, already coded in Speedy library for us to use. So basically we use a console something, console get char, console print something, console put char, like we did in the timer lab, but those are the Speedy program onto the BGA. Then we have our own write service. We program our own VGA. Okay, but we didn't program the keyboard device driver, which is a little complicated. That the SPD has for us, the get chart. But we don't really use it. We don't use it only for the experimental part. We actually use a terminal device driver to cater the user interface keyboard input ourselves. And these are the number 4, number 5, helping process. Oh, I shouldn't say that. The field gate is one. Okay, field gate is the first one. Then we have the 3 console input and 1 console input get chart and 2 console prints. So that's 4. This is 5, 6. The 5th and the 6th. Set CR3 get CR3 functions from the SPD library. Otherwise, all the codes that we build, we code ourselves inside here. Okay. Then of course this has to include some help function like those 6 inside here too. Does that make sense? Any other function you call the C runtime library is actually called back to the Linux host to run it and then transmit back the result. So it's very slow. So if you do the print function call, and that is a no-no. Okay? So that's why we need to have console print. That's the target PC print. If you print here, you print the target PC, and this library call requested by your code running over there on target PC in my OS.dri will print to the Linux host or any standard C runtime library services and syscalls are on the Linux side. So Linux side is going to do the remote running for the target PC. All right, so that's why we don't use them. If we use them, why don't we just ask Siri to run everything? Why do we need to do programming? In the future, you just, Siri, can you run this program? All right, I'll hook you up. So, your car, say, Siri, why don't you take over my car? Okay. So your car is empty. It doesn't need to be any brain. It's just remote. There's a center big brain in Google. Yeah. So all your devices, all the senior project you're doing, what do you need to do that? Just hook up to Siri, that kind of thing, and then hook up to Google Internet, let them control it. Your demo is perfect. And then your robot can dance, but it's just a dumb terminal. It's just from remote, yeah? So that could be the future, you never know, right? Every building needs to have a central brain that control all the devices, that's all you need. Why do you need to reinvent the wheel? Put another brain into this device, another brain into that devices. They don't seem to synchronize right, and they don't work right. You have this standard big brain controls everything. Yeah. So that becomes the becomes the Skynet, just like Terminator, movie Terminator, controls everything. All right, so you gotta build your own. That's why we're here, build our own. Okay, how primitive this is, but believe me, Microsoft do not want you to know this. Okay, they don't want any competitors. The less you know about this, the better it's better. Okay? They will pay me money to shut up. Don't tell them about this. Teach them nothing. Teach them just use Siri or use Alexa. Don't do it. Okay. So here's the reason why. Okay, we're going to copy from the OS translation table. 6 entries. We copy 4, and then what about 2 other entries? 2 other entries we need to know the reason. Okay. So C, we're going to prime entry, I'll just tell you the answer, 128 in the TT with the address of IP, IP. Adding 2 flags, present and what? And rewrite. Okay, rewrite. And then what about the number 6 entries? We're going to fill in prime entry 3A3, okay, in the main translation table with the page address. So it's address, of course, DRAM address. Every time we say address, we mean it's the DRAM address, not the real address. So address is a very ambiguous term. Sometimes we use it too much. So that's the 4K byte DRAM page, the first byte location, byte number. Okay. Real address of stat table, okay, the subtable, and then we should add. Okay, we should remember to add the flags, the 2 flags. Okay. All right, so the reason is the MAU is going to translate like this with the virtual address, like instruction. The first 10 bit of the instruction is the first 10 bit of this number, right? The VM start. So hexadecimal, that is 20, and then half a 0. Okay, 20 and half a 0, 10 bit. So there you can see this is 4 bit, 0, 0, 1, 0, and then 0, 0, 0, 0, and then 0, 0. Okay, and then we have half of this. So this first 10 bit is how much is this? 1, 2, 4, 8, 16, 32, 64, 128. Okay, so 128. So that means when MAU translate page numbers, people say, not our page number in the page queue. The front 20 bit are page numbers, because each one is with the starting zeros. They are the beginning of one page. Okay, so you can see the intervals here. They are page E01, E02, E03, E04, E05, E06. To translate into here, from here. Okay, so this will map to one of the pages, basically. So the translation table entry is to bear this as the location to find this, one of these. Okay, and that is used as like an array index into the main translation table. Look at it like an array. So this will be 128 as the index into that array. Okay, that array. So the TT 128 and 383 becomes the target. So how many does it have? From 0 to 123. How come we only set out these 2? Because we're going to start small with just 2 subtables, and each one can cover 4 many. But in the subtable, we're going to do the same, just 1 entry. Just point to the first instruction page and stat page. Okay, so this has 2 entries point to here and here, and this will have 1 entry points to instruction page. This will have 1 entry that has a real page number address into this page. Okay. Yeah. So basically, I'll zoom in this. Okay. So you can see the global picture is actually like this. The change like this. All right. So that's the 2 entry numbers are this. Okay. All right. And this is designed as a hardware piece by MAU. Okay, it's not that we can change this format. Okay, so out of the 32-bit, the virtual address, okay, it's gonna be partitioned into 10, 10, 12-bit, 3 parts. So this first 10 is gonna have this index, And this is coming from VM star. Okay. VM star, the first 10 is gonna be 128. Okay. From this number has a decimal. Okay. So what about this guy? This guy is from where the stack should be around, and that's the VN end. Okay, and that's where we have the VN traffic. Okay, traffic is a why? Because PCB is going to be put in where the VN traffic. Okay, so here we're going to get to that point. So the VM traffic is, where's the VM traffic? Plus this number is a virtual address where the traffic is in the virtual memory. And then the star is also where the EIP starts. And okay, so this is gonna be the VN end minus the traffic size, basically. Okay, and then add 2 integers. Okay, because we have one return null and one argument on top of the traffic, so you're gonna move down here. So beginning of the traffic is a little lower by 2 integers. Otherwise, it will be just from VNN down. Okay, and VNN down here is gonna be what could be the number? Okay. Yeah. So the VNN is 6000000. Okay, and then minus the traffic size. What's the traffic size? 48. 12 integers minus 8. So it's minus by 6. Right?
Okay.
Yep.
So what's this in binary? I mean, it has a decimal. Binary over 2 half. So that's a
1, 2,
5, 6. What's hex 5, 6? It's 3, 48. 4.
38,
It's 38. Yeah.
3.
38.
3, 3A, okay. So minus 3A. So how much you want this be? We got 7.
Yeah.
7, and then this will be
11.
12, 11.
11. So B minus 3. B.
B is 11, right?
Yeah.
Okay. So that's originally it's gonna be C, so we have follow, so it becomes B. So what about the rest? F. Okay.
5. It'll be C8.
1, 2, 3, 4. 1, 2, 3, 4. Yeah.
Have to take one.
So 8 digits. 8 digits. Okay. You will see in the end that these last 12 bits, so long as it's not too far off, it's not really used by you. I mean, you care about the first 10 and the second 10. So the first 10 to second 10 is the key. Okay. So it's by F.
It ends in
F,
C8.
B7.
Should be C.
C8.
C8.
Yeah.
A, B, C, 12. Okay, yeah. 12, 13, 14, 15.
That should be 8.
8. Possible. All right. So what is this, the 5F and a half of F? 10 bit. So that is the 0101, 1111, 11, okay. And then the 1111, the last F, we only need the first 2 bits. So basically, it's not doing the reason, it's not doing the logical operation arithmetically. You just take the first 10 bit on the surface of this number, okay, truncate like this. Usually we say, oh, shouldn't we truncate from the right side when you convert a number? But this is not convert number. Let's just take the first 10 bit and then use that as an index into here. And that's a 383. Yeah, is it 383? Maybe.
Could be, but it looks like it.
1, 2, 4, 8, 16, 32, 64, 128. If we have this plus 1, that's 128. And am I counting this one? Yeah. And then 256, So 128 minus 1 plus the 256. All right, in human term. So is that right? 127. Seems to be right, yeah. 673. Eureka, 383, okay. So you guessed it right. How did you guess that?
So the first 10 bits are gonna go on 128, the second 10 go on the 383. Right?
Oh, this is a different number. This is first 10 bit on a different number. So that is where the stack table shall be placed in here. Okay. So we know we are anticipating the MNU, okay. Well, we're anticipating MNU is going to do this. And then so we're going to put inside here the table beginning byte. The table is the instruction table, sub-table. MNU does not know all these names. You just look at when you set CR3 TT, okay, and then you will just use this to translate whatever comes. The instruction comes from here, okay. The traveling EIP is going to set here, and then the PCB of the running process traveling address is going to be set here. Okay, it's going to be set here. All right. So that is, okay, so when this is going to be loaded, the traffic going to be loaded, has this big address given to prod loader. Prod loader needs to translate that, so we got to set the CR3 first. To program the set CR3, okay, we have the set CR3 with another traffic pointer. That's what we do, okay. Before we, wait a minute, the TT, okay. This is the process TT. Okay. The process selected to run process TT. We have TT recorded here. All right. So that process needs to give MNU its translation table address before we can start the process loading. Okay. So the process can load and then load the process. When we load process, meaning we load process traffic. So we're giving the PCB traffic pointer, which is huge. We're going to set it to there, okay, set it to a virtual address. And the other function we borrowed, is the get CR3, and that returns the. We're going to use it to get the OSTT, okay. OSTT can be obtained in the kernel data initialization, okay. Kernel data initialization. So OSTT becomes the additional data structure, okay. So in here, page Q and OSTT, the new data structures, and we find 5 DRAM pages to dispense. It's going to be dispensed like this. So here, entry 128 has this address, okay, has this address, the real address of IP. All right. So MNU look at the translation, giving the CSC3 to this point, okay, the real address of TT. So this is the real address of IT, instruction table. And the second 10 bit of the instruction table is all zeros. Alright, so we see that, okay, so the first 10 bit is 128, second 10 bit is this thing here. So it's 0, 0 followed by 8 zeros, they're all zeros. So what does that mean? That means the address of the instruction table, okay, will be used with the second 10 bit to index it, and then that index is 0. So that's the entry 0 should have the address of the final instruction page. Okay? So that should have instruction page pointed to right here. Alright, so the instruction page is finally found. The instruction is copied here. Okay, instruction is copied here. My child stuff. Okay. Child stuff. Alright, so that is the real address of IP. Okay. What's not real? What's not real is the first 10 bit, second 10 bit of the virtual address. Virtual address. 32 bits. Use that as the index into the tables like an array index. So we say that's the entry number, okay? Entry number. And this is done by hardware. Okay, hardware is going to be operated by MAU like this to fetch inside the entry 128. That number is going to be used to start the IT. And then the second 10 bit 0 is going to be used as entry number 0. Alright, entry number 0. And then that is to use to find the address in the entry. Okay. The address of IP. And then the last 12 bit is used to index into the instruction, to fetch the instruction. Beginning is 0. The first instruction is 3 zeros. Okay. So that's the the last 12 bits are zeros. So that's the first instruction to fetch, and then the program counter increment. So that number is going to change using a virtual address. Okay. And then by the second token, we're going to have the entry 3A3 points to the stack table. Okay. So the address, the real address of the stack table is inside here. And then the second 10 bit of this guy is all ones. Okay? So the first 10 bit, 5F and half F, followed by that second half of the F with 2 F's. It's gonna be all ones. Okay? So it's gonna be all ones. All ones means 1023. Okay? Alright, so that's the, alright, so the second 10 bit is 1023, the first 10 is 3A3. 1023 means that MAU will use that as the entry number to find the stack page from the stack table. Entry 1023, the stack table will have the first byte location of a 4K byte page. And that is designated to use as the stack page. And we're gonna build a try frame in here. And inside the try frame, the EIP is BM star. Okay. So you have EIP, and EIP equals to BM star. Very big number. And the try frame, okay, is here. Okay. And then the argument to my child stuff, the return null is not used for child stuff process. It's gonna be here. All right. Okay, so this is the virtual address of the result of the traffic loaded. Then the translation becomes 128, 0 to 5 instruction page. And then this is 1023. This 383 is this guy. Okay. And then the second 10-bit is 1023. That is going to be here to locate the address of the stack page. And then what about the rest? Are you okay? The knowledge is very spicy. All right. So so that's the reason. Okay. So what about the last 10 bit of this guy? FCA. So what is that thing?
Offset within the page.
Yeah. So that is what do you think that address will be in terms of the 4K inside here? So what about this number? It's actually FCA. Okay. So that's the offset inside the 4K byte. Yeah. All right. So let's verify this. Is this right? So this is the how much is F? F is the
4 1s. And then 1100.
1100.
1000.
10. So that is the same address as the 10 minus the 1024 minus 48 minus 8. Yeah, in 4096. Okay. There are 4096 4K, 4096 bytes minus 56. And this would be 4040. Okay. So the byte 4040 basically. Okay. So the first byte is this one. Okay. So this one is this one. This one. 4040. Okay. So this should be 4040. All right. So the last 12 bit don't change inside this 4K byte page font. Okay. So the page address found plus that last 12 bit becomes the real address given to the cache. Okay? So the flags are 1 1. The last 2 flags will want to set. Other flags we don't care. Okay? In every entry we build 4 entries. Alright, so the last 2 flag is 1 1. All the entries of flags are zeros. So all the tables, we need to do the same thing, where the B zeros to B zero, every 4K byte page we obtain 5 pages to erase, okay, and then we can we make sure that the entries are 0. Yeah, some people suggested we should be 0 all of them at the kernel data, which is true, okay. Which is a good idea. You know, we B0 here, that's fine. If you B0 here in the exit surface, that's fine. If you B0 in the initial kernel initial data, when we enqueue 20 page numbers into the page queue, okay. But we need to B0 here, make sure that the entries are set zeros. If we didn't set a 1. Present, the rightmost bit present, okay? And when we reclaim them, we also B0 them, yeah? We can leave them alone, or we B0 them. We B0 them is what we want to do. We require to B0 them. And that can erase the translation table, main table, subtables, and the instructions and the stack. Okay, so this is runtime. Runtime well behaved, not causing page fault, that is. If it caused page fault, like the instruction, if you add an instruction want to write to a location, you set a pointer to some virtual space that you know it doesn't have. Okay, so basically child stuff plus 4K. The child stuff is here. child stuff, the address of the function plus 4K, when you set that, and you dereference it, either read or write, and then that will be beyond the 4K space, okay, beyond the 4K space. And that will come out from the virtual space, okay, that will come out into the next 4K bytes not allocated, the instruction come up, right? So that will cause page fault, okay, because the entry will be different in Q. The second 10 bit will be 1. Okay, the second 10 bit will become 1, the instruction pointer. When the instruction pointer, when the P, okay, P will become, will have a virtual space, the second 10 bit is 1, becomes 1, okay. If you say, this is this plus 4K, okay, plus 8K will become 2, okay, plus 12K, it will become 3, because that's the virtual space every 4K, okay, and the second 10 bit, is going to start to change, yeah? We say, you see the changing here, every 4K, we start to change it, the number here, 0, 1, 2, 3, okay, 4. So that's the nature of number. If you're giving a virtual address, you plus hexadecimally 1000 or decimally 4K 4096, that will jump to another 4096. Yeah? That one portion is the trim of the 12 bit, whatever this is going to have this number change. Okay, roll over. And if you add 4 meg, okay, if you say, oh, it's this guy plus 4 meg, okay, the 4 meg is going to actually power out 2 to the 20. Okay, so the meg is there's this number, okay, the 2 to the 20 is in decimal. So if you have this address, which is this point, and plus this, plus 4 meg, and that will have the first 10 bit changes. The first 10 bit will change, meaning the change is not this guy anymore. It's not 0, becomes 1, becomes 2. Whenever you add 4K, okay? And it's gonna be this guy changing, okay? This last bit changing from 0 to 1 to 2, every 4 meg. Okay? And that will cause the entry 129 to be located, alright, at 4 meg. Because one main table entry points to a sub-table entry that points to 4 meg. Okay. In this case, that not only the entry 129 causing a page fault, but also that needs to point to a sub-table, and the sub-table needs to build an entry from the second 10 bit of this offending address for the entry of a sub-table entry into that new sub-table, and then add the instruction page in. So it's not allocating a new instruction page anymore, like you increment by 4K. Okay, that changes this number, second 10 bit. Second 10 bit, you had a sub-table already. You just add into the sub-table new entries, allocate a new 4K byte, to point to the new instruction page number 2, instruction page number 3. Okay, so new instruction page can be replenished, furbished like this. Okay, furbished like this. So it's gonna be a sub-table. So this one points to needs to be a sub-table. Okay, and then the sub-table points to have an entry points to the instruction page. And that's a new sub-table, stat table 2. So 2 things need to be added, page faults, okay, not present. Does that make sense? So the procedure here, after we build the main table, we build a sub-table, okay? So then the E is that to build, wait a minute, number 5, okay, to build the sub-table IP. Okay, IP is because the second 10 bit in the VM start. That's the instruction start from here. Okay, so EIP is going to start from here. So that is the entry 0. Okay. All right, so we're going to add into entry 0. Okay. The real address of the instruction page. Yeah? Although that's a number, you can use a macro to get the address. Okay. And then with 2 flags. Same thing like that. Okay, 2 flags added. Just one entry, and then build the subtable stack table. Okay, and this is the last entry. 1023. Okay. Last entry. You prime the last entry with the address of the instruction stack page. Stack page with flags to be more concise. I'm repeating myself. Okay. So as I repeat, I get the most concise language. I hope that you understand, right? You don't need me to explain. What's SPE? SPE is stack page. You mean the number or the address? All right. So we need to record the TP. We need to record the track frame. Okay. So wait a minute. We haven't built the content yet of the instruction page and the stack page. Okay. So we're going to make, I don't want to say build tables, I say make the instruction page with a copy of child stuff. So usually we pass this, not knowing what it is, with the function pointer p, right? With the function pointer p as the source. The size is 4K, we're just indiscriminately. We don't have the size on the function. Okay. So then make the track frame page, the stack page, where the argument plus null plus the track frame from top. Okay. Okay. Coming down. So that's the same way we build it as previously. We're using real pages addresses to do these. Okay, real pages. And then did I miss anything? We need to set we need to record the PCB track frame with the VM track frame. Okay, you define constant VM track frame will be easy. Okay, will be easy. And VMN. Okay. So yeah, the calculation using VMN will be the only place that VMTF is going to be used in the macro, in the constant define. So in that place you gotta be a little careful. Okay. Other places where we mentioned the VMTF itself and the VM start, they are within 2 gig. So we don't have the shifting problem. Okay. Okay. If we're going to change our VMN to 3 gig, then we need to consider defining unsigned integer. Question?
So clarification on the VMTF calculation, on the HTML file it says 1.5 gigabytes is what we're supposed to use, but on the coding ends we're set to use 2 gigs. I just want to make sure it's...
Not 2 gig, 1.5 gig.
Okay, thank you.
Sorry about that. That's weird. VM track frame. Yeah, the using the VM end, which is 1.5. mention 2 gig, mention BMN. We already defined a BMN, which is the BMN is 1.5 gig minus 1. so it's still not going into 2 gig signed. So it will be safe if you define a BM traffic with a BMN. You got +1 to be precise though. Okay, so that's a 1 byte difference. Yeah? So it's just a byte, who cares? Yeah, if you lose a byte, it's not a big problem. If you have extra byte, it becomes a big problem. Going into the next process, going a little bit,
You'd be 1 byte off for everything.
going to next page. Okay, so argument lost 1 byte. It's not 4 byte aligned. And then what's gonna happen, who knows, And your argument is gonna be very strange. Maybe you call sick fault or something. Okay. Anyway, so do I have anything more? Yeah. The complication, you gotta be careful. I gave you the example in the coding hint too. How to use GDB to trace this, okay? You can dereference it and then trace it nicely using the GDB command, okay? Yeah, I'll just like to, if you read it, you get the idea how to debug this thing. Exit service, await child service. When you reclaim the 4K byte pages, you got to make sure to set the CR3 back to the OSTP. And yeah, so if you reboot, then the fun thing starts, okay? And you gotta look into at the end of the coding hint to get a clue, right? Alright, so the VM spaces switching is one very big thing. When the child exits first, this is because you run the fork with the ampersand, okay? You run fork with ampersand, the parent do not call wait, and then the child will exit first, become zombie child, right? And then a wait call is issued by the runtime alteration with a signal request from the parent to go to wait child subroutine to call wait child now to claim the zombie child. The zombie child has an exit code that's in the EBX of the traffic of the zombie child, but the PCB of the zombie child traffic address is a virtual one. Okay, so the runtime of the wait child service for the parent cannot access that. It will reboot. Okay, MAU will reboot.
The MAU needs this translation.
So we need to set CR3 there too. Okay, and in order to get a copy, in order to translate this big traffic address into the real traffic location, to get the EBX out, copy to a local variable somewhere, and then set the CR3 back to the parent's translation table. Okay. Okay, I guess there are lots of things that I never mentioned. I didn't get a time to mention, like the real-time kernel, like multi-core kernel, and SWAT space, the LRU and LRU. And one flag is the LRU flag inside here. For every entry main on subtable, there's an access flag. This will change by MAU, so don't be scared if you use GDB to look at the entries, somehow changed. It's not the original number. And that's because the last 12 bits are flags. MAU will set it to 1, from 0 to 1. Will flip from 0 to 1. That's the 4th bit from the right. And this, we can use this to, in the new phases, to search for those entry has flag flipped by MAU since last time. Okay, every time we reset it back to 0, and then it may flip again when we see it, like in timer service. Okay, we can periodically 100 times a second check the translation table currently in use by the ROM kit. Okay, and then what? And then see this flag is accessed the LRU count associated with that page. It points to a page. We have a count for that page, LRU count. Okay, we can reset to 0 or increment it by 1. Yeah? So the largest LRU count indicates it hasn't been accessed for the longest time. Okay, then the OS has this knowledge. And then we can build the page daemon to swap out the list recently used the DRAM pages to swap space. Okay, that's the additional disk partition set aside for the virtual memory to extend the DRAM pages into the swap space by 1 terabyte. Okay, so basically you have 1 terabyte of DRAM supporting the measly maybe 2 gigabyte, 4 gigabytes of server DRAMs. All right. So at the end of the semester is the beginning of understanding 139. So everybody can get a picture of what it means by swap space and virtual memory of the system. The kernel does not need virtual memory, okay? It's actually the process that needs virtual memory. All these virtual space run is virtual, okay? So the process itself in the virtual space of how many gig? Only portions are mapped at the time, okay? Only the runtime. So there are hundreds of virtual running processes, and each one has only portion being supported by DRAM right now. So it's this thing, and in couple with the swap partition, swap in, swap out, okay? Swap in and swap out. So they are not supported, then maybe swap out. There's another flag for that. If it's not present, it doesn't mean that it's totally not present, brand new. It could be it's in the swap, okay, in the swap it. So the page daemon or the swapper, okay, the swapper can do the swap space operation. That's another process, daemon process, to swap in, swap out. And looking at the LRU to swap out, to keep a healthy portion of the DRAM free. And then the DNA, we didn't do the direct memory access. All these can be done by this daemon process to program DMA to transfer the data in the background, kind of like streaming data in the background thing, stealing the CPU cycle, okay? But anyway, so have fun, okay? Good luck to you, okay? Have a good time.
For the final exam, should we expect it to be similar to the layout of our midterm, or?
Yeah, it's similar to midterm. It's not comprehensive after phase 5. From phase 6 to 10.
Okay.
Do you have, any data for you?
Yeah, I think I had.
Will it include cash?